Hello and welcome to this session on functional safety. My name is Ross Benton. I'm a Director of Safety Solutions. My background is in control systems engineering and I've been a functional safety engineer for just over 8 years now. In this session I'm going to be talking about what is a safety instrumented function. So let's start with having a look at what the definition of a safety instrumented function is. So it's a function that is designed to be independent of other protections, such as the basic process control system or other mitigations. And it is designed to protect against the specific hazard that we're looking at. It has a defined reliability, which can be calculated. And one of the characteristics is that it shouldn't be able to cause or initiate another hazardous scenario. A SIF is made up of 3 different parts. The sensors, which can be individual or have a set of redundancy, the logic solver, and the final elements, which again can be individual or be in a redundant configuration. Multiple SIFs can form a safety instrumented system or an SIS, where you can have an overlap of different sensing elements and final elements to produce different SIFs. So we still have to apply the independence rules when we're looking at LOPAs, but if there's different initiating events, we can have different protections that are formed by a combination of the inputs into the logic solver and the outputs. The requirements for a safety instrumented function are covered by 2 standards. The actual physical equipment is covered by IEC 61508, and that should be covered off by the manufacturer and supplier of the devices. The application of those devices into a function is then covered by IEC 61511, and that looks at how the instruments, the logic solvers, and the final elements are designed, put together, verified, installed, and commissioned and operated, and all the different things that are involved around the life cycle of looking after a safety instrumented function. So let's have a look at that life cycle. The life cycle starts with hazard and risk assessment, and this is where we identify what controls are in place to mitigate the hazards that you have on your site. We can identify with the risk assessment if there are any risk gaps that need filling. If there are, we can then specify a safety instrumented function to fill that gap, which moves us on to the second stage, which is the allocation of the safety function to protection layers. Once we've done that, we can then write a safety requirement spec. The safety requirement spec is like a instrument data sheet, but for the whole function, and there's a number of requirements around that which we'll look at later. Once we have a safety requirement spec, the designers can go off and pick their instruments and do their design of their wiring. Once we have a design and that has been confirmed that it will meet the requirements in the safety requirement spec, we can then go to installation and commissioning, and there's a validation process along with that. Once we've confirmed that installation and commissioning has been done to the acceptable standard, we then move into the operation and maintenance phase, where there is continued testing of the instruments to make sure that they're still functional. This life cycle also covers modification and decommissioning. And whilst we go through those steps, as you see on the right hand side, there are verification activities that need to be done to make sure the steps are being carried out as per company procedures and the requirements of the standard. And there's also on the left a requirement for functional safety assessments and auditing. These are the documents that will basically sign off to say that you have a certified SIL function. So this life cycle needs somebody in the company to manage it. And there should be a documented, systematic approach to making sure that all the steps of the life cycle are carried out when there are any new or changes to design. We should identify competences of the people at each step that are required for carrying out each stage, and identify the required documentation. IEC 61511 identifies different checks and measures that should be in place, and these are validation, verification, assessment, and audit. Validation is a method for confirming that we're going to meet the risk gap that we've allocated, and consists of doing some probability to fail on demand calculations. Verification is done on the HAZOP and risk assessment, and is a check to see that the process has been done properly and completely as per company standards. Functional safety assessment looks through the detailed design, checks that verifications have been done, and confirms that the design is going to work to the specification, and also goes through the commissioning and testing of the function and signs off that all the processes have been done correctly there. And finally, auditing. The audits are carried out on a regular basis at a high level to ensure that all the processes of the life cycle have been carried out. If there's any new functions, they can check that the different stages are carried out for new functions, and also for the operation of existing functions, just a check to make sure that testing and other requirements have happened as they should. The first thing that IEC 61511 addresses in the life cycle is the safety requirements specification. Now, the SRS is a document that outlines the detail of how safety functions are going to be applied. Some of the requirements can be generic to the safety instrument system, but a lot of them are specific to the actual SIF itself. As mentioned previously, it's kind of like an instrument data sheet, but for the whole function. 61511 identifies 27 different areas that need to be completed and data to be stored on. And these areas can be things like the general description of the safety instrument function and how it's going to achieve the functional safety, through to information such as describing the process measurement and their trip points, and requirements for manual shutdown. Let's have a look at the rest of the list. We have also things like maximum allowable spurious trip rates, and identifying any other interfaces between the SIS and other systems such as BPCS. So you can see here that 27 items, it's a fairly comprehensive body of information, and the idea of the SRS is that it can then be taken on to the next stage, which is design, and the instrumentation engineer can look for equipment that is going to meet the requirements to fill the SRS. And here we have an example of a SRS page, and we've organized the different requirements into logical sections. So we have a definition section, reference documents, SIF design details, and then on the next page we'd have the instrument design for the sensing elements, logic solver, and for final elements. So we've taken cross-references from the table previously. So as you can see, the first item we're looking at is the process safe state, and that relates to the requirement 3 of IEC 6511 SRS. Moving on down into section 3, the SIF design details. Required integrity level relates to SRS item 8, as does the target PFD. So we've got a good cross-reference here of how we're fulfilling the requirements of IEC 61511, along with a good detail around the reference documents of all of the different parts of the function, from loop drawings, P&IDs, operating procedures, and references to all the review documents. And here we have the second page, which has the actual function equipment definitions in. So we have sensing elements. This is a 2 out of 3 configuration with a differential pressure. And we have information around common cause failure and fault detection. and then we move into the final elements, which has the different components of the valve that is going to close off the process. And importantly as well is having a sign off at the bottom to say this has been designed by a qualified person and also been reviewed. So a safety instrumented function has two main factors associated with it: the safety integrity level and probability to fail on demand, which are related. The risk assessment has specified that we need to fill a particular risk gap to meet the tolerable risk level, and this risk reduction is represented by the probability to fail on demand. And depending on what category level of failure on demand that we get, we fit into different SIL categories. Other things that affect the SIL category are the hardware fault tolerance in the design, and this is how much redundancy that we have in our equipment, the testing requirements, and also the independence of assessors. So as we go up the SIL levels, we're generally looking for more independence. Now, meeting the PFD requirements, to calculate the PFD, we have to have equipment failure rates and testing intervals, and those are the two main factors that go into the PFD calculation. So for calculating the probability to fail on demand, as we just mentioned, you need two things. You need the failure rate of the device and the testing interval. So if we plot failure over time using the failure rate, when we first start, we know the device has been commissioned and is working, so the probability that it's failed is 0. Over time, it's going to increase. If we test, we confirm that again the device is working, so the probability immediately after that test that the device isn't going to work is 0 again, and we end up with a sawtooth plot of the failure rate of the device over time. Now, to get the probability to fail on demand, we can average that sawtooth. In practice, when we do a proof test, we can never really get a 100% confirmation that the device is working, so this sawtooth will start drifting off. So then we can do a simplified calculation, assuming that the curve of the failure rate is a straight line at the beginning of the curve. We can take that failure rate for undetected dangerous failures and multiply it by the testing interval over 2. And this gives us a pretty good approximation to the PFD average. Should be noted here that this is a PFD calculation for a single device. Once we start adding redundancy, we have to get into more complex simplified calculations. And where do we get failure rates from for devices? Well, there's a number of different sources. The source that is considered to be best is to use proven in use data from your plant. The more devices that you have for that particular type on the site, the better the reliability data is, but you need to also make sure that your maintenance records are recording what type of failure these devices are having as well, whether it's a dangerous undetected, or dangerous detected, safe detected, safe undetected, for example. If you can't find that sort of data, then there are other sources of information that can be found, such as Exceeder or a reader that gives you generic information from other plants, and that can be a good source to base it on. And Exceeder do test data as well, so you can actually get a certificate that says that this specific instrument is rated to a particular failure. The third place to get data from is manufacturer's own data, although this has to really be used with caution, as it is the least reliable. It's usually data that has been gathered from testing with clean services and will not relate directly to the conditions that you're going to be operating the device in. So once we've got a PFD for an individual piece of equipment, how do we work out the PFD for the safety instrumented function? Well, that's quite easy. All we need to do is add the different probabilities together. So as you can see from this calculation, we take the probability to fail on demand for the sensor plus the probability to fail on demand for the logic solver and the probability to fail on demand for the final element. Add those together and you get the PFD for the safety instrumented function. Now remember, if you have redundant equipment, we need to be working out the PFD for the redundant equipment before you add it, because redundancy adds a little bit more complexity to those calculations. Let's have a look at a calculation then. So for this function, we're looking at a 1-year testing interval, and the function consists of a pressure transmitter, a generic 1 out of 2 SIS controller, and a ball valve. So data we have for a generic pressure transmitter is that its failure rate, dangerous undetected, is 6.667 times 10 to the minus 3. And to convert that to a PFD value, we'd be looking at putting it through the calculation, which uses 6.667 times 10 to the minus 3 times 1 over 2, where 1 is the testing interval. And that gives us a PFD for the pressure transmitter of 3.33 times 10 to the minus 3. Now, the data we get for the logic solver was already in a PFD format, so we're being told that that is 9.85 times 10 to the minus 5. And finally, for the ball valve, the failure rate we have found is 1.667 times 10 to the minus 2 for a generic ball valve. And using the calculation again, multiplying that by 1 over 2 gives us 8.34 times 10 to the minus 3. So if we add those three values together, we're ending up with 1.17 times 10 to the minus 2. And comparing this to the SIL level values, that is giving us a very good SIL1 function. One of the other main factors that we need to consider with the safety function is the hardware fault tolerance. Now, hardware fault tolerance is an identification of how much redundancy is needed to go with the function. So if a hardware fault tolerance of 0 is a requirement, then the function can be made up of just the single devices that the design requires. Once we start needing a hardware fault tolerance of 1, that's when we need to start having redundancy in the architecture. So at least one more transmitter in the sensing element and at least one more final element, so an extra valve to do the shutoff. The reason for this was that it was identified early on in the development of the standards that there was some uncertainty in failure rate statistics, and to compensate for that with higher levels of SIL, they added this requirement. So as the SIL levels go up, then the requirements for the hardware fault tolerance get a little bit more strict. This table highlights the changes that have happened with the requirements of hardware fault tolerance from the original IEC 61511 to the latest version. The table is simplified from that in the standard and is only looking at low demand functions. But what has happened is the requirement for SIL2 has changed from requiring hardware fault tolerance of 1, so requiring redundancy in the equipment, to not requiring it. This changes with high demand mode, so if you have something operating in high demand mode, go and have a look at the table and see how it applies. There are two main ways of determining whether equipment is suitable to use in a safety function. Now, the first and most simplest way is to have certified equipment. So when you buy the safety device off the shelf, it will come with a SIL certificate which tells you what the failure rate is, and this failure rate has been determined by a third-party assessor such as Exceeder. Now, the second way of doing it is to use proven in use, and there's a few more hoops to jump through with proven in use, but the main things is you've got to make sure that the manufacturer's quality manual is in place. There has been adequate identification and specification of components and subsystems. There is a continued demonstration of performance in similar operating profiles and environments. So this is where you can get generic data from to back up your use of a particular device. And then for your own experience, you need to prove a certain volume of operating experience. And all of this can be developed over time. But so it is possible to develop a SIL function without certified equipment, but there's much more onus on the operator to make sure that the data they're using is accurate. We have three different modes of operation to consider when we're looking at a SIF, and the first one is the main one that we've been talking about, which is low demand mode, and we generally look at that as any SIF that is having demands on it placed less than once a year. So that's either because of the excursions from the safe operating of the plant is going to happen less than once a year, or we have other controls in place before the SIF is activated. However, there's some scenarios that we might consider that have a higher demand rate than that, so they more than once a year. And the third type is to say that they are continuously operating. Let's have a look at high demands and how to handle them as a safety function. When we're considering a high demand function in a risk assessment, what we do is we switch from having the function as an independent protection layer and actually consider it as an initiating event. So all of the different things that can activate and put a demand on that function, we don't consider those as initiating events anymore, and we just consider the failure of the safety function itself as the initiating event. And so then, because we're taking it as an initiating event, we need to look at it as a likelihood and not a probability to fail on demand. So the different SIL levels can be expressed then in a frequency of failures per hour. And SIL 1 changes from a PFD value of 1 in 10 to 1 in 100 to a frequency of failure of 10 to the minus 5 to 10 to the minus 6 failures per hour, which is approximately similar to 1 in 10 year failure to 1 in 100 year failure. SIL 2 goes from 1 in 100 demands to 10 to the minus 6, 10 to the minus 7, and SIL 3 equivalent goes 10 to the minus 7, 10 to the minus 8 range. Proof testing of high demand SIFs is not possible. Effectively, every time that they activate, we're confirming that the function is working. So testing isn't going to bring you any extra value. So thank you very much for listening to this session on safety instrument functions. I hope that it has helped you to develop some of your understanding of when to apply safety instrument functions, what the documentation requirements are around it, what the life cycle requirements are, and a little bit of more understanding around some of this terminology that is very different to other things you've done. Really do hope that you got something out of it. If you want to ask questions or would like some more support, please go and have a look at our contact section on our website. And yeah, thanks very much.